Welcome to video number 1 of this calculus series on my website. Today we're going to be introducing with limits and discontinuity. Now, what is a limit? First of all, now a limit is going to be the value of a function at a given point. However, what makes limits special is that it's not just at a given point. Now, before I can go into this, we need to talk about what a discontinuity is. Now, we talked about this in the Algebra 2 section, and you probably talked about it in class a little bit. A discontinuity is going to be a point where a function is undefined. So, for example, let's say we have this graph here, okay, and we have this function coming in here. However, we have a hole. When we try to plug a value into this function, we're not going to get a value here. So when we put an x into the function, this point is going to be undefined. So what we do with limits is we try to find what this is. What is this value in this hole? Alright, now another kind of discontinuity we can have is we can have an asymptote, horizontal or vertical. Now that'll be something like this. We'll put this dotted line here. And now we see these lines, as they go up to infinity, are never going to get to this point. They're never going to reach it. They're going to get infinitely closer, but they're never going to reach it. Now we also might have a horizontal asymptote. Say, for example, we have this function that's going down here, right? And say we have an asymptote here. This function is going to get infinitely close, but never touch this line. Alright, so these are our discontinuities. However, a limit can take place for a standard function. Now, the way we notate a limit is, let's see here. We are going to have alright, so this is going to be denoted by this. So we're going to have the limit as x goes to n, n being the values that we're trying to find this at, of f of x. Alright, so what this is saying is as this x value here gets close to this value n, that's the value we're looking for. So let's do a few examples just so you can understand the concept here. So let's go to equation. So what we're going to have here is we're going to have the limit as x goes to 5 of x squared x, sorry about that. We're going to have the limit of as x goes to 5 of x squared minus 7. Now, what we're going to do here is we're going to assume that this x value has become 5 because there's nothing discontinuous about this function. Right? There's nothing discontinuous. So what we can do here is we're going to substitute 5 for x. So we are going to be left with a 5 squared minus 7, which will be equal to 25 minus 7, or 18. So we've evaluated our first limit. Does not seem too bad. Now, let's change this up a little bit. So we're going to have this equation, and we are going to have the limit as x goes to 3 of, and now let's put a fraction in here. So this is going to be the limit as x goes to 3 of x squared minus 9 over x minus 3. Now, we have a problem here. Here we were able to just plug 5 in for x and get a value, just like that. However, if we were to substitute x for 3, we would be left with a 0 over 0. Now, what are we going to do about this? What can we do about this? Alright, what we can do about this is we're going to go back to some Algebra 2 stuff and we can factor this. Alright, so we can factor this. So we will be left with, when we factor this, we can have x minus 3, x plus 3, if you remember difference of perfect squares, a squared minus b squared, and this is going to be over ax minus 3. Now what do you notice about the numerator and denominator? Well, this x minus 3 and this x minus 3 can divide out. So we're going to be left with the equivalent function, x plus 3, right? Alright, so now all we have to do is substitute the value 3, since we have the limit as x goes to 3, and this is really hard math. So we're going to be left with 3 plus 3. Now I know this is a challenge, but I think it's 6. So we evaluated another sort of weird, funky limit. Alright, now let's talk about some other discontinuities. Now, well, or special cases. If we are left with 0 over 0, that means that we need to simplify. We need to simplify to find a finite value. And there will be a way to do it most of the time. Most of the time. There will be some occasions where it's just a bizarre function. But if we are left with 1 over 0, now we might think, oh, this is ridiculous. Okay, but this is going to be equal to infinity. Now, why infinity? Because I can multiply 0 infinitely many times and almost reach 1. Well, and not reach 1. So this is going to go to infinity. But that is not to say that 1 divided by 0 is just infinity. The limit, here actually let me write this out. So the limit, use this equation writer, the limit as x goes to 0 of 1 over x squared this is going to be equal to infinity. Where is infinity? And, oh, there it is. Alright. Now, why am I using an x squared here? This is another point to get to here. So, the reason I'm using an x squared on the bottom is because if you have a positive side of a function approaching one value and the function from the left approaching a different one, the limit does not exist. Now, for this, now you understand the basics of this, but now we're going to have right and left limits. Alright, so what does this mean? Alright, this means that a function, now let's say we have this function here. Alright, so we're going to have this function coming here and here. Alright, and then it's going to do its own thing off the graph. Alright, now if we try to evaluate this limit, there isn't just one point here, it's 2, right? So when we evaluate the limit from the right side and the limit from the left side, these are going to be 2 different values, okay? So what we say when this occurs, right here, when this occurs, is the limit does not exist. Now, what we can do is we can see that this function this way does have a value. This function this way does have a value. So, what we're going to say is we're going to evaluate these individually and say this is the right hand limit and this is the left hand limit. Now, the reason I put 1 over x squared for that was that function is going to have this on the left side and this on the right side. Now, even though these do not approach a finite value, you can see they're both going to infinity. There's that 1 divided by 0. However, since with 1 over x, that value x is going to be negative on this side, we are actually going to have this function coming here and this function coming here. One will be going to positive infinity and one will be going to negative infinity. Alright, so these are some of the basics of limits here. And this should be all you need to do the practice problems. We will revisit these after derivatives.